going to start class and start recording. By the way, once again, nobody came to the office hours, which on Monday I've scheduled from 3 to 5. I'm beginning to think maybe that's may overlap too many classes, so I'm going to change it. Instead of 3 to 5, we're going to make it 4 to 6. So office hours on Monday are going to be by Zoom, and they're going to be 4 o'clock to 6 o'clock. You should look at the class website frequently because I update various things on the website. In fact, if I bounce over just for a moment to the website, let me go to the website. Okay, just to show you what, let me move this down. So what does get, first of all, you should look at the errata for the second edition. So I keep track of mistakes and change them. The class notes, this file here, it's frequently updated. And so you can see now, in fact, that it contains chapters 8 and 9 and 10, actually. Also, there are the handwritten notes from the iPad. These were from the first couple of weeks of class. These were the second couple of weeks of class. These from the third set of class. And these are the homework assignments. These are the various videos that I put on YouTube. Okay, so I don't think we need to go into that anymore. So let's start chapter 8. Chapter 8 is a short chapter. It doesn't mean the material is unimportant. It just means that that I guess we don't talk about differential equations. I'm sorry, we don't talk about integral equations very much in physics classes. And in fact, the only time I recall integral equations being discussed in a physics lecture was years ago when people were reconsidering scattering theory in all kinds of sophisticated ways. And in particular, Steven Weinberg gave some lectures at Brandeis during what was then the Brandeis Summer Institute for Physics. And he gave 2 sets of lectures. One set was his, concerned his very useful descriptions of quantum fields of various spins. And that material later turned into his part of his book, his series of books on theory of, what is it called? The Quantum Theory of Fields, Volume 1. A good fraction of Volume 1 was in those summer lectures. But he also discussed integral equations. It's the only time I saw them discussed in physics. And so the light emphasis that I've given them is a reflection of that. And frankly, a word to the wise graduate student would be, or to the ambitious graduate student would be, keep an eye on the physical problems that you're concerned with and see if maybe some of them are can be treated with integral equations as opposed to differential equations. The thing about integral equations is that they contain more information. That is to say, they contain the boundary conditions, at least partially, and they're much more suited to numerical solutions. And we'll see that today, I hope. So let's suppose we have just a first order differential equation, ordinary differential equation. Here it's inhomogeneous, linear. Nonlinear equations are very hard. Anyhow, if we integrate that, we immediately get the integral equation that looks like this. And you see the boundary condition is there. U of x vanishes, U of x just is equal to U of a because the two integrals vanish as x goes to a. And so this is an integral equation due to this first order differential equation. Now, if we have instead a second order ODE and it's inhomogeneous because of the term r, we can convert it into an integral equation by integrating once. And when we integrate once, the left-hand side just gives us this, and the right-hand side is just that integral. And then we can integrate again, and this is just a constant, so we can put it on the other side, and it contributes an x minus a. U prime integrated gives u of x minus u of a. We put the u of a on the other side, and then we have a double integral. And I changed y to z and integrated up to y, and then integrated dy up to x. So this is our double integral here. Now, Cauchy, of course, did a gazillion things, and in particular, he has a way of converting a double integral into a single integral. And of course, that's an extremely useful thing. And in fact, as I said, in physics courses, in physics textbooks, the way physicists think about physics, they're focused on differential equations. I think it's very possible that integral equations should be used much more in physics than they are. Anyway, Cauchy's identity is actually a special case of his more general formula, where he can take an n-dimensional integral and turn it into a one-dimensional integral. Now, of course, the case in which he did the way he did this, or his formula applies to a function of a single variable. So you're integrating f of xn, and then you get an integral of f of xn that depends upon a single variable, xn minus 1. Then you integrate that, and you get a function of a single variable, xn minus 2, and you integrate that, and so forth. So it's not that he can take an arbitrary multiple integral and turn it into a single integral. It's that he can take a multiple integral of a function of a single variable and turn it into a single integral multiplied by a monomial. So in particular, we've got a double integral here, and it's a double integral of a function of one variable. And so bingo, we can use Cauchy's identity to identify f of to do that, we identify f of z as the thing inside the square brackets, and then what we get is that instead of this expression, we get applying Cauchy's identity, we get an integral over y there. And then what we can do is we can integrate the first term by parts. And if we do that, then we get this long integral. And then you can decompose this by choosing a kernel, defining a kernel, k of x and y, as p of y plus x minus y, q of y minus p prime of y. Those are things, that's this term and this term. And where was it? Well, anyway, p of y. And f of x equal to this, namely these terms out in front. And you can then rewrite the thing this way. There's the kernel. And you can then write u of x as f of x, which is this long thing, plus an integral of the kernel times u of y dy. And so this is an equation that's the integral equation corresponding to this general second order ordinary differential equation, which maybe if R is non-zero, then it's inhomogeneous. If you have a Sturm-Liouville differential equation, second order, you can turn it into an integral equation. You once again use Cauchy's trick, and what you do is, let's see, you start out with this equation, you rewrite it in this way, you integrate once and you get this expression. There's a cancellation, you get this expression. You integrate again, and then you get this expression. And now you use Cauchy's trick again, and you get p of x, u of x is f of x plus an integral kernel u of y. F of x is this, and the kernel is that. We can apply this second version. We can apply it to Legendre's equation. Then we would have p is in Lagrange's equation, p of x is 1 minus x squared, and Lagrange's equation looks like this. P vanishes at x equal to a, and so f of x also vanishes, and so f of x, you see, is p of the lower index times the square bracket. And so f of x vanishes, and the formulas then, these formulas give Legendre's integral equation in this form. In the case of Bessel's equation, p of x is x, and this is the self-adjoint form for k equals 1. And p vanishes again at x equal to a, so f of x also vanishes. And since q is n squared over x, we get this expression here. You might notice that all of this, none of this, in fact, none of this is in the book. What happened was I wrote a certain version of this section 1, and the editors at Cambridge University Press, without saying a word to me, dropped completely the self-adjoint version of this, and then took the version that I just wrote for you here. They took that and put it as an exercise, and so they compressed the version that I had. They also generalized it, though, because I went immediately to a self-adjoint form and left out the general case, which I then just wrote up today and just presented to you. It'll be in the class notes, which will be on the webpage sometime tonight. Now, what I've got to go through now is a bunch of definitions, and please forgive me, but there's no way to say these definitions other than to just read what's in the text, or at least my version of the text. I haven't checked what Cambridge did with them. So suppose we have an equation that looks like this: an integral. You're looking for the unknown function u of y or u of x, and it occurs in two places, and then you have an inhomogeneous term. Okay, this is called a Fredholm integral equation, and always this thing that multiplies the unknown function. This is always called a kernel, and I keep thinking of some commercial food company that features its kernel. Actually, my oldest son became a colonel recently. He's a medical doctor, a doctor in the army, and became a colonel recently. Anyway, but that colonel spelled with a C. This one is spelled with a K, kind of the German way of spelling. Anyway, if this is an inhomogeneous Fredholm equation of the second kind, and if f is 0, then it's a homogeneous Fredholm equation of the second kind. And in both cases, this lambda is a parameter that, especially in the homogeneous case, it has non-trivial solutions only for certain eigenvalues. That may also be the case here. And in fact, it probably is. In fact, when we do the section on numerical methods, we'll probably see that. Now, if lambda is 0, but f is not 0, then it's called an inhomogeneous Fredholm equation of the first kind. So this expression like this was the first kind of Fredholm equation. And you see, this is the kind of equation that is very much like a linear algebra problem of the kind that you'd like most, because this is written as an algebraic equation. It's Ku equals F, so U is K inverse F, if K is non-singular. Finally, if lambda and F are 0, then what we have is a homogeneous Fredholm equation of the first kind. And this is a kind of special thing. This basically says that U has to be chosen so that where K is positive, it occurs as much, it weighs the part of the kernel that's positive as much as it weighs where it gives as much emphasis to the positive part of K as to the negative part of K. These are all linear because they are well, they're called linear because they are linear. U occurs only at first power, not U squared or square root of U or log U or e to the U or something like that. What would these look like if they were nonlinear? Well, if this were, U squared or something, then, well, in this case, you'd solve for U squared, and it'd be linear in U squared, and then you'd take the square root. Over here, if you had U cubed or something, again, you could regard it as linear because you could take, you could say, well, it's U cubed, solve for U cubed, and then take the cube root. And here also, if this was, U to the alpha, and that was U to the alpha, you just solve for U to the alpha. So if the unknown function, if you change the power of the unknown function, the thing still, even though it's technically nonlinear, you can still basically, I think, solve it about as easily as in the linear case. And that's probably true of differential equations also. That is to say, if you have, for example, suppose you have an equation, say P y prime prime with a minus sign plus Q y plus R equals 0, say. Well, you can solve that for y, but if your equation was of the form P y to the alpha prime prime plus Q y to the alpha plus R equals 0. Well, this is the same thing. You just solve. What you would do is you would switch and you'd solve this first equation, and then you'd set your solution as y to the 1 over alpha. So, for example, let me maybe put suppose your equation looked like this, then it was z to the alpha, z to the alpha. Well, you just set y equal to z to the alpha, and then you go up and you solve this one. And then once you solve that for alpha, you then set z equal to y to the 1 over alpha. That's a 1 over alpha. So again, the thing that makes nonlinear equations difficult is not that the unknown function occurs to a funny power, but that it occurs in the equation raised to different powers. That's the killer, different powers. So we just did Fredholm. Volterra ones are the same as Fredholm. It's just that they're a special case in which the kernel is causal. So in other words, Heaviside step function occurs. So in other words, this says that u of x only depends upon u of y for y less than x. So in this integral, only y's that are less than x occur because you have theta of x minus y. And so once again, this thing is an inhomogeneous Volterra equation of the second kind. You set f equal to 0, you get a homogeneous Volterra equation of the second kind. And then if you don't have a lambda u in the equation, you then have the first kind, and it's ku equals f. This is the standard linear algebra problem, basically, if you discretize x and y. And if you blow away f, then you get a homogeneous Volterra equation of the first kind. And so later on, I'm going to be talking about Fredholm cases, although there isn't very much of a later on in this chapter, because as I said, this is a very short chapter. Now, these Fredholm and Volterra equations are linear, and so you can add solutions. So if you have, for example, solutions of the homogeneous equation look like this with the same eigenvalue, then you can add them together and you still get an eigenfunction with the same eigenvalue. And so what you can do is then you find all the solutions all linearly independent solution eigenfunctions for that eigenvalue, and then you have a complete set for that eigenvalue, and then you find all the eigenvalues, and then you have a complete set of solutions of the homogeneous equation. And then the difference between any two solutions of the inhomogeneous equation is, of course, a solution of the homogeneous equation, because if you have, as we've seen, well, I was about to, previously what we saw was we had L1 is equal to some inhomogeneous term R, and L2 is equal to R, then L on Y1 minus Y2 is just 0. And so you can add together all solutions of the homogeneous equation, you get something that's complete for the homogeneous solutions. And then what you can say is that the most general solution of the inhomogeneous equation would be y is equal to a sum of the yi's times alpha I plus some particular solution of the inhomogeneous equation. That is to say, Ly particular equals R. So this is the most general solution then. That's for differential equations, but we have the same thing with integral equations. If we have integral a to b, for example, k of xy, u, maybe I'll use a different index, alpha, of y dy is equal to lambda u alpha of y plus f of x. So this is an inhomogeneous Fredholm of the second kind. I don't know why I had I and j here. Oh, I is inhomogeneous. That's a stupid notation. I really must do something about that. You take the, you subtract the two inhomogeneous ones, and then that's the homogeneous one, and so you have integral a to b of k of xy u of, say, 1 of y minus u 2 of y dy, and that's going to be lambda u1 minus u2. Let me just leave out the y. And so the differences of the inhomogeneous, of the solutions of the inhomogeneous equation as a solution of the homogeneous equation. And so you write the most general inhomogeneous solution as a particular solution of the inhomogeneous plus the most general u alpha. I'll say a alpha u alpha of y. That's an a. I think actually I'm going to change that and just call it a C alpha U alpha, and it's kind of hard. There's no friction between the Apple Pencil and the Apple iPad. It's hard for me to write well. So this is the general solution. Particular solution of the inhomogeneous equation, the general solution of the homogeneous equation. Now, one advantage of the integral equation form, and by the way, one I suppose the real reason, sort of lurking in the background of why integral equations are more useful than differential equations, is that you've already done a lot of the work, or some of the work, when you've converted the differential equation into integral form. Because after all, you have to, if it's a second order equation, you have to integrate twice, and you get something that is then the integral equation, Fredholm or whatever. So you've done some of the work. It stands to reason that it should be a more useful form and something easier to work out. Let me see if I can move this over just a bit. Okay. Well, in particular, this thing is very much in the form, it's just begging to be done numerically, because you've got, let's talk about the homogeneous Fredholm equation of the second kind. And so you've got an integral of the kernel xy, u of y dy is lambda u of x. Well, this just looks very much like an equation, sum of over I, k of x alpha, say, yi, u of yi is equal to lambda u of x alpha. And I don't know why I did an alpha there. So let me come in here and get rid of that alpha subscript. I don't think we need that. Okay, so this is a matrix equation for each x, fix x, say. So this is then a matrix equation. K u is equal to lambda u. And if we do make, I guess to make it a true matrix equation, I would have to let that be a j, say. And then we have an xj here. So this is k j I u I equals lambda uj. So it's a matrix equation. K vector u is lambda u. So we're looking for the eigenvalues. Hold on. I want to just switch to blue. We're looking for the eigenvalues and the eigenvectors of a particular matrix equation. And so that's something that MATLAB or someone, it's a hard problem, you can use Fortran because you get a lot more speed. You can just solve this. And of course, matrix equation of this form, well, if there are here, for some reason, I summed from 0 to n. I don't know quite what went wrong in my head that I went from 0 to n. I mean, you know, it's, I guess it's that computers, I think, like, they prefer to go from 0 to n, but people prefer to go from 1 to n. So I think I should switch to 1 to n. In any event, this is an n by this. In this case, it's an n plus 1 by n plus 1 equation. It has n plus 1 eigenvectors and eigenvalues, and the eigenvalues are the values of lambda that make the determinant of k minus lambda I vanish. And MATLAB can, of course, do these basically instantaneously. And the way you can see that this works is what you basically have here is some L equals 0 to capital N, and then you have K sub KL. Oh, that was stupid. Little k, big K. Yeah, that was dumb. Hold on, let me just fix this. I'm going to change this notation slightly. K I L U sub L is equal to lambda U sub I. And so this is then sum L equals 0 to N, K I L. Hold on, let me just I L minus lambda delta I L U L equals 0. So you can rewrite the first equation, this one, you can turn it into that form. And then this is a matrix equation. What this is saying is that we have an eigenvector of this matrix that a vector that is mapped to 0 by that matrix. Well, that means that that matrix must have a 0 eigenvalue, and that means that its determinant has to vanish. And so we have the determinant of K minus lambda I is 0. And that's what we learned back in chapter 1. And as you know, MATLAB is very, very good at those equations, solving those equations. And we could apply the same technique to the inhomogeneous Fredholm equation of the first kind. Then we would have Ku integrated is F. And so that in matrix form, it would be K times U is equal to F. And if K is non-singular, so if determinant of K is not equal to 0, then U is equal to K inverse F. Let me rewrite that as K inverse F. And once again, so if you discretize this thing, then you have a matrix equation. And if you apply it to the Fredholm of the second kind, you get a matrix equation that looks like inhomogeneous. And then what you have is this equation here. And so that's of the form, when it's discretized, is Ku plus, Ku is equal to lambda U plus F. And so what you've got is K minus lambda I times U is equal to F. Well, if lambda is such that the determinant of K minus lambda I vanishes, then for such lambda, you can't invert. So this is, you want to stay away from such lambdas, but, and we'll call them the lambda alphas, eigenvalues. So in other words, the eigenvalues are Ku equals lambda alpha U, alpha equal to, well, it'll go from 0 ... up to capital N, because there will be capital N plus 1 eigenvalues, lambda alpha. And so what you can say then is that for such lambdas, the equation has no solution, because you would just have F equal to 0. So what you do is you choose lambda not equal to one of these lambda alphas, and then you write U as K minus lambda I inverse on F. And I went on here to say, well, you could use a pseudo inverse and so forth. I think we can just as well skip that. And let's focus on this business of integral transformations. And this, of course, is something that some of the mathematical geniuses who lived 100 or 200 years ago worked out for us. What you can do is you can take, what you do is you suppose you have an equation of this form, namely that you have an equation LU plus CU equals 0. So we're rewriting it, and this is the homogeneous linear case. Let's suppose L is something like d2 dz squared plus b t dz plus c, and a, b, and c might be functions of z. And we can say z is x plus iy. Okay, so that's what we're basically doing. And so then the choice is, this is a choice, so we choose. We choose a kernel K of Z and W that's analytic in both variables. And we then write U of Z as an integral over a contour K of Z and W times some V of W dW. So this is known, and chosen. And also the contour. The contour C is known and chosen. But we don't know what V is. I don't know how to get it. Okay, but and so the original thing was, what's U? We don't know what U, we're looking for U. So then we say, well, we're going to write U as an integral. We're going to pick a contour and pick a doubly analytic function K, and we're going to rewrite U as this. So we have to find V. That's the situation. And now, so what we do is we say, well, let L be a differential operator with Z derivatives, which is what we had to begin with, but no W integrals. So we can write L on U of Z is then equal to L on this contour integral of K of ZW, V of W dW. But now L is a Z thing, Z derivatives only, so it can come inside and hit K of Z and W. And it only hits K, it doesn't hit V, because V is a function of W. And so our original equation, if the equation was LU plus CU equals 0, then, so if it was LU plus CU equals 0, then what we have is LU is this structure, and let me get to maybe here green. So LU is this structure here, and CU is just an integral of K times V, because so to get, well, that's the wrong one. To get CU, we just multiply this by C, and we get a C there. And so putting them together, what we have is integral along a contour of L, which is a Z, involves Z's, functions of Z, derivatives with respect to Z, plus C times K of ZW, V of W, dW equals 0. Okay. Now you might say, oh, we've made it more complicated than it was because up here it was just very simple, and here we've got this complicated structure. Well, you often have to take 2 steps backwards to go forward by 3 or 4 steps. And what you next do, so this is the trick, in order to actually, so far we've just massaged an equation, a differential equation, converted it to an integral equation, and haven't really done any work yet. The next step is to find a linear operator M that is a W integral, a W linear operator. So we want to say M, let me write that more carefully. M on K of Z and W is equal to L K of Z and W. Now, this is a W operator and this is a Z operator. So this is the big trick. And this is the non-trivial trick. If you can do that, you then get an integral equation, just substituting for LK, MK, what you have is an integral over C, M, and I'll write W, on K of Z and W, plus C, which is just a constant or an eigenvalue of sorts, K of Z and W, V, that's the unknown function of W, dW equals 0. So this is our integral equation. And it involves W integrations. And we can integrate by parts. And the trick then, remember, we have the contour at our disposition, and also we have K. K can be any analytic function of both analytic and Z, analytic and W. The contour, arbitrary. So the next thing is you choose C so that when you integrate by parts over W, the boundary terms vanish. And then what happens is V is then simpler. The equation for V is simpler than the one for U. And now that I just want to make sure that it's actually where the hell is this thing? All right, typeset. So that's a typo here. This for U. It's the equation, resulting differential equation. It's an equation for V. I erased the wrong thing. Okay, so some examples, and the great mathematical physicists of the past showed us how to do this in 3 different ways. Fourier did one way, Laplace another, and Euler a third. And what they did was what is it that they did? Well, they chose a k, the analytic function, or the bi-analytic function, or the doubly analytic function, k of z and w. They chose that cleverly. Then they chose a contour that was clever. And in particular, what Fourier did was he said, well, this k of zw, it's going to be e to the I zw. Well, it's obviously analytic in z and w. And he then took an integral. He chose the contour to be integrating on w from minus infinity to plus infinity. And one can say, well, we're integrating how? We're integrating over the real line if we take w just to be real. But it could be an integral anywhere. But the nice thing about integrating over the real line is that you then get, you naturally get 0 at both ends. That is to say, the boundary conditions often vanish. The boundary terms often vanish. But you can choose the contour differently, just as long as you go far enough out so that the things, the boundary terms vanish. What Laplace did was he said, well, let's let k of z and w be e to the minus zw. Again, it's doubly analytic, and you then get the Laplace transform. And now he says, well, you have to integrate from 0 to infinity. You don't want to go to negative values of w. And then Euler said, well, there's nothing left for me except this choice, z minus w to the a. And this occurs in some applications of Cauchy's integral theorem, and also in it's the Cauchy integral formula. In other words, what is going on? I don't know what is happening here, but I'm not getting any response here. It's possible that the pencil is out. Ah, yes, the pencil is out of juice, and so I need to choose. I'm charging it. So, in other words, remember Cauchy's integral formula, well, it's not all right. Cauchy's integral theorem. Anyway, it's that f of z is an integral going around the point z of f of z prime divided by 2 pi I times z prime minus z, and that gives you f of z. So now I'm charging this. I don't know what level we're at here, but it should be. So let me just go on here. Another example is Bessel's functions. The differential operator is L of z, in other words, is this structure here for Bessel's equation. And what I presume it was Bessel who chose this doubly analytic function, or doubly entire function. And the question is, you then look for an operator M such that M on K is L of K, M being a W, function of W and its derivatives, and L a function of Z and its derivatives. And lo and behold, the simple thing of minus d2 dw squared works, because then M on K, K being this, you take minus the second derivative with respect to W of this structure, and that gives you Z squared, the second derivative with respect to Z of K, plus Z times the first derivative with respect to Z of K, plus Z squared K. And of course, these were strokes of genius. These were not obvious things. And so what Bessel did was to rewrite the original integral equation, which was of this form. It then looks like this, and now this is an equation for W, and this is what you can then do, since you can integrate by parts, and this is the second W derivative of K, so you integrate by parts. The first term, KW, in other words, it's K double prime V, and you integrate by parts and you get K prime V prime. And then the genius stroke is you choose the contour so that the boundary terms vanish. And then you integrate by parts again, and you get V double prime plus lambda squared V. And then you get these structures here, and you choose the contour so this vanishes. Then you just have a simple differential equation. This is a harmonic equation. And it's much simpler than Bessel's equation. And the solution then is V is the e to the I lambda W for any complex lambda. And it's an entire function of W. And so what is our Bessel function? The Bessel function then is K of Z and W. And remember, we chose K to be this exponential. V we chose to be e to the I lambda W, and so we get this structure here. So now we have a representation of the solutions of Bessel's equation as an integral. And so if real Z is positive and you have any complex lambda, then you choose a contour that runs from minus, let me get this off that one. So you go up from minus infinity, or actually minus pi, minus infinity, up to minus pi. Then you go over to 0, and then you go, let's see, I did it wrong. It's you start at minus I infinity, you go up to the origin, then you go to minus pi, and then you go up to minus pi plus I infinity. And then the boundary terms all vanish, and what you wind up with then is this particular contour that I just described, e to the minus I z sine W plus I lambda W. So it's this structure here. The choice is the minus sign. Convention says you multiply by minus 1 over pi, and this is called the first Hankel function. The second one is you again pick real Z positive, any complex lambda, but now you take another contour, and this contour starts with pi plus I infinity down to pi over to 0 and then down to minus I infinity. That's called C2, conventional factor out in front, and you do the integral, and that's the second Hankel function. And the integrand here is an entire function of Z and W, and consequently you can deform the contours like crazy just as long as you leave the endpoints fixed. And you can then verify that H1 of lambda is equal to H2 complex conjugate. So the two Hankel functions are complex conjugates of each other. We somehow just blasted through that how shall I say that, chapter really quickly. So let's just go on to Legendre polynomials. And while I'm at it, let me say that the MATLAB program that I wrote, I was originally going to do 20,000 terms. I said, well, let's do 40,000. And for 20,000, I got this expression. But on the other hand, I then rewrote it for the first 40,000 terms. And if I do, well, I can show you what the result was. By the way, it took 57 hours, so 2.5 days on my computer. And let me show you let me bring up the new version. It's an 8 there. Oh, no I. Okay. And you see this one went to about 6,500, and I chose to go from minus 0.05 to plus 0.05. In the new one, I just had to go from minus 0.02 to plus 0.02 because there's not much of interest occurring here. But then let me show you what the change is. And what we'll see is that this 7,000 gets quite a bit higher. Boom. Okay, so now it's gone up to 13,000. And of course, this thing is actually very, very sharp. And if I had used, here, let me just see if I can, oh, I don't have the MATLAB program written in front of me. No. Anyway, what I did was I used the conventional line thickness, which is 1. If I had used 0.5 or 0.1, you would have this peak here would have been skinnier, because I think it is skinnier. But in fact, the step size though was 0.00. What was it? Now I don't. Well, all right. Here, let me show you. Since I've shown you all this, I might as well show you what the MATLAB program was. And I think, as I said to you before, if you do run a MATLAB program, you might want to use not a for end loop, but a par for loop, which makes the thing parallel. And just to show you the program, you see, instead of going to 10,000, I went to 20,000, but it's actually 40,000 because I chose one of the to do delta of x, not delta of x minus a half or x minus 1, because or in other words, I'm doing delta of x minus y for y equal to 0. So one of the arguments is 0, and the odd Legendre polynomials vanish for x equals 0. So I was able to skip all the odd ones and just do the 20,000 even ones, and that's the same as doing 40,000. And the spacing was 3 zeros and a 1. So in other words, it's 1/100th of this distance. And or no, I'm sorry, it's 1/100th of this distance, or equivalently 1/100th of that distance. So actually, it can't be very different from that. Anyway, so that's just to verify for you, and to what that shows you, of course, is that it shows you that the Legendre polynomial is complete, and you could take any complete set of functions and create a Dirac delta function by doing such a sum. Now, the monomials x to the n are obviously complete, but they're not orthogonal. And so what Legendre did was he constructed some polynomials that are orthogonal, and he also normalized them. So first of all, he wanted them to be orthogonal. And one way to make them orthogonal is to say that each Pn is orthogonal to all monomials of lower order. And that way, Pn would be orthogonal to Pm if m is less than n. And that basically does it. He also imposed not a normalization in the sense of integrating the thing, but instead saying Pn of 1 is 1. So that's another thing I could have done. I could have done delta of x minus 1. That would have been equally quick. Or, well, no, I would have had to have done then every actual value. So that would have been twice as long. It would have been like almost a week. So he imposed the normalization condition and the orthogonality condition, and then it turns out they're unique. And I plotted the first 20 here and on the cover of the book. Well, I don't think they did all 20 on the cover of the book. They did maybe the first 10. They're quite nice, I think. If you do lots of them. Anyway, the coefficients of the nth Legendre polynomial, well, they have to satisfy all the conditions of orthogonality. And so xm times each of the coefficients, it would then be xk, the integral of xk plus m integrated, you get this expression here, and you integrate from -1 to 1 is the condition of orthogonality. And so these are the n conditions of orthogonality. And then there's a normalization condition, which is that you see here, Pn is a0 plus a1 x ... plus an xn. And so the normalization condition is a0 plus a1 plus an is equal to 1. And so in particular, you can make these Legendre polynomials. You just said P0 is the constant, has to be 1, because P0 of 1 has to be 1. And then you pick P1 of x as linear in x, but it has to have coefficient 1 because P1 of 1 is 1. To make P2, you set n equal to 2 in this expression, and you then get 2a0 plus 2a2 over 3 is equal to 0, and that's for m equal to 0. For m equal to 1, you get this expression. And then the normalization condition is that the 3a is summed to 1. And you have 3 equations, 3 unknowns. You get P2 is 3x squared minus 1 over 2, and so forth. P3 is that. P4 is that. Pn plus 1 is odd in x, and consequently vanishes at x equals 0. That's the thing I used to oops, where the hell did that go? That's what I used to simplify this sum. And so I think we mentioned earlier the Rodrigues formula. The one way to compute Legendre polynomials is to apply Leibniz's rule to what's called Rodrigues's formula. And this is rather a remarkable formula. It says that Pn is the nth derivative of x squared minus 1 to the power n. And of course, x squared minus 1 is x minus 1, x plus 1. And then what you can do is you can use Leibniz's rule that we learned long time ago, namely that when you have a high derivative of something, you have k derivatives of the first term and n minus k derivatives of the second term, and you get this expression here with this n factorial over k factorial and minus k factorial, then squared, the binomial coefficient squared. And if you set x equal to 1, well, then you get this expression. This 0 raised to a positive power vanishes. So the only term that survives is the term when k is equal to n, and that gives us this expression here, which is 1. If you use Rodrigues' formula, you can eventually get these expressions. And in MATLAB, you do mfun quote p quote nx, and you get the numerical value of pn of x. Where of course you put in not x, but you put in 0.5 or 0.23 or something, and then you get pn of 0.23. To see that the polynomial is orthogonal to the lower ones, well, you just combine Rodrigues' formula with the requirement that this integral vanish, and what you have then is you can integrate by parts n times, and this guarantees that the surface terms vanish. And but then you have n derivatives of x to the m where m is less than n, so you get 0. So Rodrigues' formula satisfies the orthogonality condition and the normalization, and therefore it's the correct formula for the Legendre polynomials. You can also show that the inner product of two Legendre polynomials is this integral 2 over n plus 1 delta nm, and that gives you that's the orthogonality. That's the orthonormalization relation. One of the things that absolutely amazes me whenever I see them is the generating function for Legendre polynomial, for anything. The idea that somewhere in mathematics there's a generating function for a whole set of special functions, I find to be quite remarkable. And these things are called generating functions. The generating function for the Legendre polynomials is this thing here. And it's a generating function because it's equal to a sum t to the n times the nth Legendre polynomial. And what is Pn? Well, it has to be the nth partial derivative with respect to t at t equals 0 of g of t and x. And to see what that might be, we use a logarithmic series. And well, I don't know. I think this is getting fairly deeply into the weeds. So I think maybe since we're almost out of time, that I'll stop at this point, because you may have just, I may have tried to put too much stuff into your heads today. We've blasted through chapter 8 and made a good start on chapter 9. I'm going to try to say some things to you tomorrow about Fortran, but also to do some examples. I haven't used Fortran for about a year, well, in a serious way. And what you need to do Fortran, of course, you need a compiler. And so then the question is, where do you get, well, G-Fortran is the GNU project provides excellent software, and they give you an excellent compiler, but then you also need a library. And what I'm going to try to do tonight is to download the Intel library, and it's not only its compilers, but also its library of functions. And I think it'll have many of the special functions that you need to use Fortran effectively. You need more than just the compiler. Well, we're basically out of time. For those who missed the colloquium last Friday, it's on YouTube now. And I'll try to put the link on the department's website. Anyway, so have a nice evening, and I'll see you tomorrow at tomorrow it'll be 5:30 to 6:20. So I'm going to stop sharing now and